All right, we're picking up the problem here, and we're doing the cantilever beam. We're going to look at the I. We're going to start in the enter the data section. We decided that our E was going to be 1,000. We decided that our property of each beam was going to be a length. He has a length followed by the I. Length of 20, followed by an I of 2. Now, there's nothing else there. Before we do this, we're going to save it as Beam001. So you'll have record of this. We're going to put a uniform load on here. I have one element, and with 10 being the answer to that. The node and the deflection. Known node deflections need at least one if the slope is unspecified. Otherwise, you need 2 if no slope is specified. We only need, that node 1 is going to have no deflection. We're going to node at least one. Okay, node known slopes. We have node 1 is going to have a slope of 0. Force applied. Now in ours, I guess I could put node 2 and 0. We'll just do that there's no, and node 2 and 0 as well. You might be able to do something different. The resolution I was playing with earlier, so let's just make it 20. You run it, and you get a solution like that. Okay. Now, what I want to do, I tell you what, I should, just out of curiosity, make this a minus. Run it again, and I think it just didn't plot anything. So here's what his deflection's supposed to be, or what he says his deflection is. Looks kind of like this. So let's take a look at this. Now, before we get all the way done here, we have we have these set up as subplots. What I'm going to do is add my own. Add a compare plot. And what I'm going to do is disconnect it from the previous. And I may move it to another location later, but for right now, I'm going to say X is going to go from 0, length of say 0.1 all the way to 20, which is the length of this beam. And then I will say Y is equal to. Now, before I do that, I'm going to do this. LEN. Maybe I should come up here and do this. Length is 20. And I'll just say this. LI for the length. EI we'll put together equals 1,000 times 2. WI, which is the load, which I considered to be 10. And then I said, from the other equation, WI times XX squared divided by 24 divided by EI divided by LI times 2 times LI squared. I'm picking this out of that equation that I had. 2 times LI minus X, and then you have to square that. Oops. And then what I want to do is produce another figure and put, there's figure 10. And for that matter, I don't want this thing to be copied around, so I'll call this figure 1. Go down here, plot, and I'm going to plot XX versus YY. Let's call it YY. Okay, let's run this again. See what I get. I get an error. That's the first things I get. Oops. Let's run it down to there. This, if hit an F9, evaluate that selection. This, evaluate that selection. 201. Oops. Let's try this now. Okay, I think I'm okay now. Save it, run it, complete it out. Put a minus there. So already I'm suspicious about this because that doesn't look normal. Well, I did not like the solution that came up with, but I found a better one. Let me bring it up. So here it is. Looking at deflection of a cantilever beam, and we're going to double check this. So what I'm going to do, go to the American Wood Council. Here, let's see. We're going to go down to I've gone too far. I need to go about. Okay. Just use the. Okay, there it is. So with your x coordinate moving from the tip of the beam, you get this equation, which I'm going to go ahead and use. And I'm going to change my boundary conditions to match it, just so that I trust them a little bit better than the solution I grabbed somewhere else. So here's what I'll do. Go ahead and change this out. Let's see. 24 EI. That's a scalar times x to the fourth. So here's what we're going to do. XX to the fourth minus 4 times length of the beam to the third times XX here plus 3 times Li to the fourth here. Now we're not going to get the, let's take a look at it. This is not exactly what we're supposed to get. One, the deflection is occurring on the right. This one, the deflection is occurring on the left. But that's a simple swap. And the way I'll do it is, instead of changing my boundary conditions, I'll do this. There's a flip, but let me test it first. Okay, so I've got a value YY. Whoops. I still have the value YY in here. So if I do a flip YY, we need to do a check for the flip. So it turns out, okay, so for some reason it didn't record what I did there, but here I went in and took his solution, the finite element, and the exact solution. I ran them, and this is what the difference was. So in here, there is a difference between these two, which is cause for concern, because there should not be a difference. So how do I remedy this? I need to get a more accurate solution, or say that was not accurate enough. How do we deal with that? First point you got, okay, let's take a look here. Get rid of this. And you have a moment diagram that looks like this. When in fact, if you really look at this, that doesn't make sense. The moment diagram this point should exist over here. So I need to remedy this, so to speak. So how do we do this? Well, in finite elements, just like the other ones, the 2D and the 3D, we found we needed more and more elements. Thing is how do you generate, given his data set here, how do you generate that? Well, here's what I'm going to do. I'm going to take the data he is sending into his own code, and I'm now going to work that over. So now I'm going to just take his code, and in my particular case, I am going to break it to the point that I need, instead of one element, I'm going to need, say, hang on, I'm going to say the length 1, 2, 3, 4, 5, 6. How about let's just do this. 6, 7, 8, 9, 10. So if I have that, one element, two elements, 3, 4, 5, 6, 7, 8, 9, 10. I believe I did that. So now I need this uniform load placed out there 10 times. So there are 10 elements now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, hopefully the thing will catch me. Node 1s, those are going to stay the same. We could leave these the same. And let's see what we get. Okay, what you'll notice is now the exact solution and the approximate solution are pretty close. And if you look at it, excuse me, it appears as though the moment equation does do what it's supposed to do. The shear equation, though, looks choppy. What it means by choppy is this really should be like a straight line, but it's not. And as a result, it is what it is. The slope equation is just the derivative of that, and so on and so forth. But the key here is the deflection itself. If you looked at that case that I wrote, and it's already scanned, but I don't like what I did on the bottom end. But it's too late now, and I'm not going to go back and change it. The hang on. If you go through here going after the Google Drive, what I'm saying is this is your project. Give it a second to come up. This equation has a shifted X distribution. It's not quite what it should be. So instead of this equation, I should have gone to this American Wood Council and picked up this one, where the X measures from the tip of the beam. Either case, the point is this is a fourth order equation. Whether you pick it up with the X coordinate originating at the tip or the base, it's still equal to a fourth order. You'll see a fourth order right here. There's your fourth order. If you go through all the rest of them, here, look at this one. Well, look at one that's a little bit more realistic. Okay, find one. Okay, so here's a simply supported. If you take a look, here you have x squared with an extra component here, x squared with an x. So this is the third order. This is x squared here with an x sitting over there. This is a third order. All of them are third order. And when you get to this, you even get worse because you have an x here, an x squared. So this is fourth and this is fifth. The reason it's fifth is because instead of that load being uniform, now it's linear. So you just increased your order there. Here's another one where it should be fifth order, x, and then x to the fourth. That's a fourth order. This one's too much to even think of. Here's another one that, if you look, you have an x, and then, well, you have an x here, x to the third. This gives you fourth order. So anytime you have a uniform load, you get a fourth order solution. Here's the fourth order for simply supported. Finite elements is only capable of doing third order. In order to get the fourth order, or an approximate fourth order, you have to put more and more elements in there. And so there's a typical case where you're doing that. And when you're comparing it, that's really what you should be comparing, is the deflection. And in fact, all I did is I set this up, I went down to the very bottom and I added a comparison plot, and that's all I did. So I figured out the equation. Then of course I did it from the wrong I did it from the wrong orientation, so that's okay. So I will leave this out there as Beam001, and basically I'll put another one out there shortly.